Hello students, I am Dr. Tanmoy Bishwash. I welcome you all in my channel Chemistry, the Mystery of Molecules. So today we are going to discuss a very interesting name reaction as well as important name reaction, because many times you can find some MCQ appearing related to this name reaction. So that is Shapiro reaction. Okay, this reaction is very useful for conversion of carbonyl group into alkene, better to say substituted alkene. Okay, where is the substitution? See here. So this is the carbonyl compound. In presence of this aryl sulfonyl hydrazine, you may consider this is a substituted hydrazine. So one part of hydrazine is available for reaction, then reaction with butyl lithium LDA, and finally electrophile or proton, which result this final product. Okay, this may result in cis or trans depending on the substitution. So a simple question comes that we have here, what we are getting, carbonyl to alkene. Previously we have read many reaction where this transformation could be possible. So what is the importance of this transformation compared to the existing method? Okay, so in order to answer this question, let's discuss about the existing methods. Generally two types of reactions are very famous for carbonyl to alkene preparation. One is a reduction of carbonyl first, and second dehydration. Okay, so this is actually the dehydration. So reduction could be done using sodium borohydride, lithium aluminium hydride, even hydrogen transition metal catalyst. Those things fine, we know it's very fine in details. And second step is dehydration. Dehydration could be done directly, like direct in presence of heat or concentrated H2SO4 like H plus. Okay, so this is, or you can think that it could be this OH could be converted into a relatively better living group like Cr, Cl, chloro, or good living group like bromo or iodo, then base mediated elimination possible. By the way, in both cases, for example, in case of concentrated sulfuric acid, it involves through a carbocation mechanism. So rearrangement of carbocation is possible. Okay, I have discussed, and by the way, I have discussed many reaction about this chemistry. Okay, previously I shall provide the link in the description box. You may go through them if you want to learn. Then second is that OH2OCl, OH2Cl, or even tosyl OH to OTS, other OH to Br, this thing possible, because after that we can do elimination. But elimination or substitution or complementary reaction, so there are lots of questions. Even when we are dealing with elimination, we have to take care of many factors. Another type of method, that is OH to OAC, like then pyrolysis, and actually this is a pericyclic, this reaction proceeds through a pericyclic mechanism but require high temperature. Okay, for that reason there is another modification, that is acid, instead of acetate we can prepare xanthate, and for that case relatively lesser temperature is enough for this conversion. But all these have some individual limitations. Okay, so this is the point number one. Another technique is the conversion of carbonyl to alkene through Wittig reaction, or Wittig reagent means this phosphonium cation and this carbanion. So in this way possible, and the driving force, please remember that driving force of this reaction is formation of triphenyl phosphinoxide, which is a very stable molecule. Okay, because of phosphorus oxygen strong bond due to back bonding. Okay, fine, we have understood that what are the existing methods. Now let's discuss little bit about the role of reagents, because it will help us to learn little in details. So see, generally for this reaction, butyl lithium, or better to say tertiary butyl lithium, so this is actually tertiary butyl lithium, or this is actually LDA used. Why? Because they actually, we know they are poor nucleophile, and additionally they are poor nucleophile but very strong base. Okay, so poor nucleophile, so we know that basis, when there is a chance of proton abstraction, there are some chance of substitution, and that could be eliminated by two factors. One is hard center and second is bulkness. Okay, because when the negative electron species is bulky, it is capable to selectively abstract the proton because it is a smaller in size. Okay, fine. So it's actually very strong base and poor nucleophile, and additional advantage of being bulky is they abstract less bulky proton, and this thing you will find the property of LDA or tertiary butyl lithium very clearly. For example, N-butyl lithium, like this one, they can act as both base or nucleophile depending on the situation, but tertiary butyl lithium is selective as a base, not nucleophile, because of the bulkness associated with this 3-methyl group. Okay, so a simple simple strategy. What happens that first hydrazone, means this aryl sulfonyl hydrazone is treated, means you make this is actually a sulfonyl chloride. You may see if you have this methyl, this is tosyl chloride, and if you react this with hydrazine, it results this hydrazone. And just look at this molecule. In this case, one side is blocked, so that part will not react, and this lone pair is involved in the resonance with this H double bond O. So only this nitrogen part is available for the reaction, and we know the hydrogen reacts with carbonyl and undergo a dehydration, means elimination of water, to result this hydrazone formation. This is a derivative of carbonyl, and this hydrazone actually responsible for this Shapiro reaction. Interestingly, for this purpose, if there are two types of proton, for example here, which this proton is more bulky, whereas this proton, this methyl proton, CH3 proton, which is less bulky, this thing, and if you do the reaction with one is very strong base like LDA or butyl lithium, whatever, then this less bulky proton, means this one abstract and get a less substituted alkene, and this is actually, this product is actually KCP or kinetically controlled product. So less substituted alkene produced in Shapiro reaction, and that is kinetically controlled. And by the way, interestingly, if you don't use a very strong base and means mild, relatively weaker as well as not that much bulky, then what is, then the abstraction of this proton is possible. Okay, and actually this happens, and it resulted in more substituted alkene. By the way, if you look at the stability of alkene, more substituted alkene is relatively more stable. That's why this product is called TCP or thermodynamically controlled product, and this reaction has a special name, that is Bomford-Stevens reaction. So this is another name reaction which we will discuss in some other videos in future. So please be careful. Remember that base has a very important role. This LD or butyl lithium, its bulkness determines the product, that is the less substituted alkene. Okay, fine. And another part, in case of hydrazone, we need to provide a special care. For example, if you take a simple hydrazone, means simple unsubstituted benzene derivative, means benzyl sulfonyl chloride derived hydrazone, this one, versus means 2,4,6 triisopropyl hydrazone, which one is preferred? Obviously this one is preferred. Why? The question is, just look at the molecule, look at these two molecule. In case of this benzene derivative, okay, simple unsubstituted, there are two orthohydrogens, and we know that when such kind of group is attached, for example the orthohydrogen where if one position is attached to electronegative atom and have some facility of coordination, like in this case oxygen, the directed ortholithiation possible. So please remember this name, directed ortholithiation is possible, and so we get the corresponding lithium derivative, organolithium reagent, and for this purpose these two two oxygen has a very important role they can do. And why this is possible? Because during the reaction we use butyl lithium in excess. Will come why and how much needed. So for that, this unexpected orthodissociation possible. So how we can avoid this? If we block this, and this blocking is possible by simple like isopropyl group. Okay, by the way, interesting point is that this 4 number, this para blocking is not essential, but when we do para blocking we have a symmetrical substrate. For example, if you look at this substrate, if you look at this versus this, the tri-substituted one means this one. If we do any aromatic electrophilic substitution like sulfonation, only one type of position is there because 3 are symmetrical, whereas if you do that thing in this molecule, means this second molecule, there is a 2 chance and it is highly expected that the sulfonation will occur at this para position. So that is the reason why we use this tri-substituted. Okay, so fine, actually the property is directed by these 2 orthoisopropyl group. Okay, fine. Now let's discuss about the mechanism of this Shapiro reaction. In this case, first step, as we told, that hydrazone formation via a ship base reaction. Fine. After that, base needed, and now we will learn how much base needed and why that needed. So first, actually here slightly greater than 2 equivalent base needed. Okay, why? Because when we use organolithium reagent, we try to use slight excess. We try to use slight excess than stoichiometry. Okay, stoichiometry. Why? Because we know during that they are very reactive reagent. During the reaction, if some moisture from air or from solvent is there, that will quench the reagent, so reaction will not be complete. So slight excess. For example, if you theoretically need 2 equivalent, we will take 2.1 or 2.2 equivalent. Okay, so this thing we generally take, it's a general trend. So here why 2 equivalent needed? Because first of all, there is one NH proton here and there is one CH proton. By the way, if we compare the acidity, generally the NH proton is more acidic. So first this NH proton abstraction will occur. Actually this is, you may consider this is actually a waste of one equivalent reagent. You will understand why. Waste of one equivalent BuLi. Okay, fine. This is, and second step, what happens after this abstraction? The second proton abstracted. By the way, after abstraction of this first proton, this negative charge is delocalized efficiently with this SO2 AR group conjugation. Okay, so fine. And second step, what happens? That this proton, actually this is a alpha of carbonyl, actually imine. So we know that they are sufficiently acidic, and so LDA abstracts, or butyl lithium, whatever you do, so that abstract this proton, and this is a enolate type generated. Okay, so enolate generated, we know that such kind of molecule is resonance stabilized. What do I mean by that? For example, this can come here and it can come here. So in this way you may consider that the negative charge is stabilized. Then this. Okay, by the way, one interesting information is that just look at here, both nitrogen having negative charge, and negative charge means not only, actually this nitrogen has 2 lone pair, means what do I mean, it has 2 lone pair and this has 2 lone pair, so severe lone pair repulsion happens. So actually what happens, that this lone pair pushes here, consequently this bond pushes here, and this sulfonyl group leaves, and ultimately what results, this diazar derivative. Okay, and we know that diazar compound where nitrogen double bond is there, they are prone to some decomposition. Decomposition means elimination of nitrogen gas. And how this can happen? So this negative charge could be pushed here and the negative charge will come here, and in this case nitrogen gas eliminates. Okay, and that is a very favorable process. Why? First of all, this nitrogen molecule has nitrogen triple bond, so it's a huge amount of energy is released, and second is gas, so it comes out from the system, so reaction can proceed in the forward direction. So after this step, what this result? This results a vinyl anion. Okay, so this thing is nothing but vinyl anion, and this is the very important step of this reaction, because this vinyl anion provides us a wide number of opportunities for different product formation. So let's discuss this, how many type of product could be possible. The most important thing in case of anions, what do we think? It's a quenching. So this quenching could be, generally we do work up using dilute acid solution, but this is actually a vinyl anion derivative, very reactive. So acid is not essential, only water is essential. And if we do, we know that water has a delta H plus proton, and this carbon ion abstract that proton and resulted this molecule. This is alkene. What was our target product. Now second, interestingly, instead of water, if you use D2, then you can get deuterium substituted alkene, and this is a very interesting. See, this deuterium has a bond with this vinyl carbon, and actually this protonation or deuteration both are acid based reaction, where the carbanion, means vinyl carbanion, act as a base and the water molecule or D2O molecule act as an acid. Similarly, so we have discussed this acid base property, but we know that carbanion can act as a nucleophile. Okay, so this can act as a nucleophile also. Vinyl anion is a nucleophile. So, and that's the thing, what happens, this nucleophile can attack an alkyl halide via SN2 fashion, and it may result this substituted alkene derivative. So this is actually example of nucleophilic substitution reaction. And finally, if you instead of such kind of direct SN2, you can do other reaction, like if you take dimethyl formamide, NN diethyl formamide or DMF, what can happen, that this negative charge can attack here, and it can open up, it come back and pushes to leave this NET2 minus, and ultimately what it result? It result an aldehyde. Okay, and actually not aldehyde, better to say alpha beta unsaturated aldehyde or alpha beta unsaturated carbonyl, which can act as a Michael acceptor. And these Michael acceptor are very important in synthetic organic chemistry, because it shows a different type of versatile reaction, and I have discussed this Michael addition reaction previously. So if you want to learn the application of these Michael acceptors, you may read that video, I shall provide the link. And finally, what actually we are getting in this reaction, previously we have started from a carbonyl, okay, and ultimately we are getting alpha beta unsaturated carbonyl derivative. So you may consider this is one kind of homologation reaction, okay, homologation reaction, that type of. So this is another versatility or synthetic application of this method, like name as Shapiro reaction, which is nothing but the application use of the vinyl carbanion. Okay, fine. So let's discuss few examples in order to complete our understanding. So first of all, this is the hydrazone preparation from the carbonyl and hydrazine. After that, 2 equivalent butyl lithium, actually better to use 2.1 or 2.2 slight excess. Okay, and what happens in this case? So if you use 2 equivalent butyl lithium, first point, the first equivalent is used to quench this nitrogen, and it results in this nitrogen anion. And why second equivalent is given? Because second equivalent is needed to abstract this proton and generate the corresponding enolate type. Okay, now question is, previously in case of Shapiro reaction, you have observed that these undergo instant other elimination, first of all first hydrazine, second nitrogen, to produce the vinyl anion. But see, in the reaction medium there is a electrophilic reagent, and iodine is a good leaving group. So what happens, that this negative charge attacks here and iodide leaves. So this is, you may consider as an alkylation reaction. Okay, so now right now what we got a new alkyl derivative. By the way, a question may come that there were two nucleophile, one nitrogen nucleophile and second means another is carbon based nucleophile. Why reaction happened from carbon? Because carbon nucleophile is softer in nature than this nitrogen, and second, nitrogen is attached to a bulky group, that is SO2 so attacking is difficult. By the way, I have already uploaded a lecture about nucleophilicity and nature of nucleophile. If you have any doubts in this concept, you may visit that link, which I believe will be helpful. Fine. So so we have understood how to prepare this product. Now question, what is the next? See, next step, another one equivalent butyl lithium is given, and actually not so here one equivalent is enough. So what it does, it will abstract a proton from here, and another thing, butyl lithium means generally tertiary butyl lithium. Okay, so it acts as a base, and ultimately what it will result. So in this case, after proton abstraction, like you know the mechanism, so I am not writing that thing again. If you feel any difficulty, I suggest you please go to the back slide and clarify again. Okay, so this is the vinyl carbanion attached to this lithium plus this, and we know that iodine is a very good electrophile. What happens? These negative charge attack this iodine molecule, and this bond breaks, and ultimately what we get? Iodo substituted derivative. Okay, so this is example number 1. Second, in this case, just I am not going to explain, just you remember proton abstraction will happen from less substituted side. Okay, so there are two sides, this and this, and interestingly in this molecule only hydrogen available here. This is a bridgehead position and no hydrogen is there, and remember that alkene CC double bond formation at bridgehead position is very difficult because it is associated with huge amount of ring strain. So ultimately this vinyl carbonyl will be generated. So if you react with water, means it will be quenched, or if you react with alkyl halide, then it will be alkene substituted this double bond. Okay, this is very easy, no need to explain in details. But interestingly this example number 3 is little difficult. So what we can think, as usual, based on our concept, after 2.1 equivalent butyl lithium hexantimida, see everything is given. Okay, so what it will result? It will first result alkene at less substituted position. Fine. So this side, this double bond is the least substituted, and negative charge will come here. Fine. Negative charge will come that place where the hydrazone is produced. See, in this case similar, the carbonyl, where the carbonyl group was there, the negative charge will come at that place. Similarly here in this carbon the hydrazone is there, so negative charge will come here. And next step, what will undergo? This means this is actually also a vinyl lithium salt. It undergo addition reaction to the CC double bond, and what it resulted, it actually this is not a general type of reaction, but for in case of butyl lithium such kind of reaction occurs. So it attacks this double bond and it's open up, and see here a ring formation possible. What is expected to the ring number 1, 2, 3, 4, 5, and this methyl should be this CH3 minus out of the ring. So first of all, this it will attack here, it will open and ultimately result in this compound. Okay, so this is a carbanion, so it can act as a both base and nucleophile. So if you react this with proton, it will undergo just quenching, and if you react with E plus, let's draw the product of E plus. So this product will be obtained, or in case of proton there will be a hydrogen. Okay, so this is the product. So this is very interesting. So by the way, in every reaction we are using greater than 2 equivalent of better to say tertiary butyl lithium or LDA. Remember, dealing of butyl lithium or LDA like strong base in a very excess amount is dangerous. There are few incident which resulted in a great loss regarding the use of such kind of drastic reagent. And how this could be avoid it if you can use catalytic amount, and that is the interesting concept. So let's discuss the catalytic use of butyl lithium to carry out such kind of reaction. So in order to go inside details, just you need to first understand where the reaction, where the excess reagent was consumed. The first equivalent of butyl lithium was consumed to abstract this NH proton, okay, and second was CH proton, means this one, this alpha proton of the carbonyl. So this, and ultimately we got a vinyl anion, which is also a significantly strong base. Okay, so just if we replace the, so if we replace the NH proton with a alkyl group, so first equivalent could be quenched, and second is that we can avoid the other, because if the vinyl group is, we know the vinyl anion is sufficiently basic that it can undergo alpha proton abstraction of carbonyl. So this is a smart choice where you are regenerating the carbonyl. See how, see, look at this molecule. Okay, so where, see, the actually this is also a hydrazone, and the hydrogen attached to this nitrogen was replaced by a means alkyl group. So no first equivalent point, the requirement of first equivalent butyl lithium we have handled. Now second equivalent were needed, this proton abstraction, and actually for this reaction 0.1 equivalent LDA is taken. Why? Because first LDA abstract this proton and generates the carbonyl, means this one, the second one. After that, what this thing do? So this thing follows the same process and ultimately resulted in this vinyl carbonyl, and the carbonyl will be generated where that carbonyl was present, means the hydrazone. Okay, and after that this can act as a base to abstract the alpha proton of the carbonyl again. So what it will result from here, it will result again this is the nitrogen, this is the pH, and here the carbanion will be generated. Fine, and again the reaction will continue in this way. So this is actually a catalytic amount. So what we have achieved? We have achieved alkyl lithium from 2 equivalent to catalytic, that is 0.1 equivalent butyl lithium or LDA, whatever. So in this case of this example is associated with LDA. So this is called a smart selection of substance. Okay, substrate, smart selection of substrate. And as a student, I always expect that you people also try to think logically such that you can avoid this risk factor associated with this chemical reaction, because it is highly desirable that we need to do reaction, but we need to be very much careful about of safety, because first our target is to save the humanity, and for that purpose we need to do this. And during this process, if we get eliminated, that's not an profit. So we need to be perfect, or we need to have the win-win situation from both sides. Okay, so we have learned an interesting topic today. So in conclusion, what total we have learned? First of all, carbonyl group to substituted alkene conversion is possible by the Shapiro reaction, and this reaction is carried out at relatively lower temperature and in basic medium. Okay, what is the advantage of basic medium? So acid sensitive group if present in the molecule, general method will result something else. For example, carbocation method, base method, this may hamper, but in this case, if there is no acid sensitive molecule, so that will not be a problem, because we are using strong base. If there is no acid sensitive molecule, the base will react accordingly. Fine, no problem. Additionally, what we are using a very strong and bulky base in this case, and if we don't use, what it will result? It will result mixture of alkene like both TCP and KCP, and actually this reaction resulted KCP, means kinetically controlled product, because it results in less substituted alkene. Okay, and in this another interesting achievement, the deuterium introduction to the vinyl carbon is possible. I believe it's a very interesting thing, and such kind of deuterium incorporation is very useful while you are doing mechanistic investigation study. Okay, so this was up to the today's discussion. Thank you everyone for watching this video. If you really like my teaching, then press the like button and write your opinion in the comment box about my teaching. And if you think my teaching is worthy, please share these videos with your friends such that they can also enjoy the benefit. And most importantly, if you think my channel is deserving, then please subscribe and press the bell icon such that you get notification of every single video I upload. So stay happy, stay blessed. See you in my next video.